Okay, so resuming our discussion of waves, we're now going to see how waves relate to the tropical Pacific to be part of the story to do with El Nino. And what Enso is versus El Nino versus La Nina, what the relevant feedbacks are, the primary being something called the Bjerknes feedback, and generally reminding ourselves of how upwelling works in the equatorial region. And this is really a story of how upwelling varies that has to do with this large-scale phenomenon. So we've covered fast surface gravity, internal gravity waves, and deep and shallow water. Now we've already talked about larger, slower waves, astronomical forcing, Rossby and planetary waves, Kelvin waves. Today we're going to talk about how those get applied into a particular phenomenon of interest. So why, you might wonder, are these large, slow waves excited? Well, wind forcing has a mean and a stochastic component on kind of days to week time scale, well, from gust time scale of seconds to minutes up to the synoptic weather component. But there are also periodic forcing mechanisms like solar, the diurnal cycle, the seasonal cycle, the orbital cycle, and perturbations to gravity, tides. El Nino is similar to this, and then it has a lot to do with the seasonal cycle, but it also has features of the weather variability superimposed on that. So it's not as predictable as that. It gets excited by a lot of different phenomena, and it's locked to the seasons. So we'll get to how that all works out. So what do we need to remember about waves? Well, we remember our phase speed, our group velocity, about non-dispersive and dispersive waves, wavelength, wave number, angular frequency, phase speed, this whole game that we have with this kind of a superposition like this. And we remember a whole mess of dispersion relations that we talked about for non-dispersive, plane waves, surface waves, short surface waves, long surface waves, internal waves, long internal waves, Kelvin waves, and Rossby waves are all the different characteristics that we've talked about. As we've also discussed the fact that the Kelvin waves are relatively fast. They're kind of like a gravity wave in their speed, whereas the Rossby waves are quite a bit slower. And we saw that in this video where we drop a blob of water, the Kelvin waves run away. This is a rotating channel on a beta plane, so it has the beta effect. And now that blob has formed a anticyclone and is slowly drifting westward. So this is the beta, this is the Rossby and Kelvin wave response to an initial perturbation. Okay, so this is the pure wave part of it, but we're going to think about Rossby and Kelvin waves in a different way, in the way they relate to El Nino, which is going to be a much more interesting, realistic way rather than this kind of idealized example. So remember, we talked a little bit about the dispersion relation of Rossby waves, that there's this, last time we talked about this. So this is the frequency in this direction, wave number in this direction. So for the longest, slowest waves, we've got westward propagation in both the group and phase speeds. Phase speed is always westward because it's positive in this quadrant, negative in this quadrant. So phase speed is always negative, but group velocity can be eastward out here once you get over the crest, and the slope, or out here once you get over the crest, and the slope reverses direction. Remember, we're thinking about Rossby waves as being an anomaly of vorticity and or sea surface height that has this rotating sense, and so it's like vortices advecting each other. And then the equatorial Kelvin wave, we talked briefly about. Let's remember how that works. If we set V equals 0 at the equator, the same way we set U equal to 0 at the coastline when we did the Kelvin wave discussion, we find one Kelvin wave solution in the northern hemisphere that matches to one that decays in the southern hemisphere. And so it's like the equator looks like a coast on the right to the northern hemisphere wave, and the coast, the equator looks like a coast on the left in the southern hemisphere for an eastward propagating wave. So if we look at the combined equatorial dispersion relation, we see the Rossby waves here, Kelvin wave here, and these are in the large scale, low frequency stuff. El Nino is large scale. It's the whole Pacific almost that it's involved. and at least half of the Pacific at a time, and it has low frequency that takes multiple years or at least months for these wave-like parts to do their business. And just as a reminder, we're thinking about Kelvin wave having this dispersion relation, Rossby waves having this dispersion relation down here. These rotating gravity or Poincaré waves that are not fitting on the page very well are these up here and these down here. These are much faster. These are typically super inertial. These down here, the Kelvin and Rossby, are sub-inertial. They involve geostrophic balance. And don't forget that there's reduced gravity. So in the G here and the deformation radius here could depend on the surface deformation radius, or they could depend on the picnic line, G prime, and the smaller deformation radius of the first baroclinic mode. Those will be much slower than the barotropic modes, and those in fact are closer to what gets excited during El Nino. Okay, so here are the goals for today. We're going to talk about why the tropical Pacific has the structure it does under normal conditions. Why does it have strong variations? Namely, there's a positive feedback. How do Ekman and Sverdrup play a role in this? And how do Rossby and Kelvin waves play a role in this? Okay, so let's take a look at the complicated structure of the Pacific. We have two gyres, and we have also this series of countercurrents and currents that go back and forth across the equator. And some eastern boundary currents as well that are due to these both being upwelling zones off of Peru and off of California. And let's remember how upwelling works at the equator. So if we have trade winds going from the east to the west like this, we tend to blow Ekman transport off of the equator. So there's upwelling driven by a westward easterly trade wind. And if there is wind blowing along the coastline, so southward in the northern hemisphere, northward in the southern hemisphere, you also drive upwelling along the coastline as well. And so if we go back to this, we expect there to be a northward wind that's supporting the upwelling and the eastern boundary current off of Peru, and a southward wind off of, at least seasonally, off of the California current. It's making the California current itself. That's the geostrophic current that's related with the upwelling zone all along here. And then there is trade winds from the east to the west here on top of this complicated series of currents near the equator, which leads to upwelling primarily along the eastern side of the Pacific. So if we take a look at what this looks like, it's pretty easy to see. Sorry, the Pacific is divided in half by the projection they've chosen here. But you can see there's a lot of productivity over here in chlorophyll in both the coastal upwelling zones off of Peru and California and the equatorial upwelling zone here. They are anomalously cold. You can see the cold tongue, as it's called. It has this link down to the Peru current. And in some seasons, when there's a La Nina going on, you get particularly cold. And then you can see the seasonality is pretty strong, but also off California, it's a little bit colder here in the upwelling zone, at least in some seasons. Okay, so here's the normal conditions in the equatorial Pacific. The easterly winds tend to rise when they're over a warm water anomaly, causing rainfall and convection. And then they loop back westward aloft and then drop back down over land and then go and do a circuit like this. This circuit is called the Walker circulation. It's sometimes this location of this convection and the location of this subsidence vary quite a bit in time in between normal conditions and El Nino and La Nina conditions. But this is a schematic that gives you the rough idea. And the convection is located over the warm water. So the cold tongue, which we just mentioned, is this region of equatorial upwelling, which really brings lots of cold water to the surface right at the equator on this side. On the western side, there's something called the warm pool, which is typically warmed by the very warm solar radiation that's coming in. So you get an east-west temperature gradient at the surface. That east-west temperature gradient actually tends to help these winds do their thing, to rise over the warm and to move from cold to warm like this. when you have winds in this direction, it pushes the water toward the west. And okay, remember, we're not talking about Ekman here. We're talking about right on the equator with no Coriolis force, no F equals 0. So when you push under winds, under those conditions, the water goes in the direction you push. Well, it doesn't just keep going forever. In fact, it builds up a pressure gradient pushing the opposite direction. So we know a sea surface high pressure gradient to a sea surface low has to do with, we tend to get that when we have warm sea surface high, low sea surface low, and a thermocline or a pycnocline that's tilted underneath. So we have a sea surface high over here in the warm pool, a depressed pycnocline consistently with the warm pool, so it means the cold water is farther away. Here the thermocline is up near the surface, or even outcropping as it does along the coastline of Peru. The upwelling is drawing up cold water from below the thermocline or near the thermocline, which makes the cold tongue. There can actually be substantial upwelling in the warm pool as well, but it's not drawing water from below or near the thermocline. It's drawing relatively warm surface waters that are getting replaced laterally. Okay, so some facts about El Nino. El Nino is an anomaly in the equatorial Pacific winds, sea surface temperature, thermocline depth, and atmospheric convection. So all the features that we just talked about here are all changing under an El Nino. It's the largest climate variability of the sea surface temperature on Earth after the seasonal cycle. It's typified by warm eastern Pacific temperature, weakened easterly winds, flatter than normal east to west thermocline tilt, deeper than normal thermocline, atmospheric convection and precipitation anomalously centrally located in the Pacific. So that convection is over the central Pacific, and it occurs in about a 3 to 7 year time scale. Here we go. Let's take a look at this movie. No, not movie, just image. This is showing sea surface height and elevation and sea surface temperature of an El Nino. It's sea surface height, and it's the sea surface temperature anomaly. So you can see all across the Pacific, there's this enormous wedge of warm water that is sitting right where the cold tongue is supposed to be. This is in November, right before the peak of the 97-98 El Nino, which was one of the largest ones that ever occurred, or at least in our records. Up until 2015, 2016, this was the largest one that had ever been recorded. It depends on which metric you use as to whether this one or that one was bigger. You can also see that there's a cold anomaly up here in the North Pacific, which is an example of teleconnections, and their cold and warm anomalies over here. This El Nino feature is so large that it actually changes the weather patterns almost worldwide. And so that leads to other cold and warm and wet and dry anomalies around the world. We'll look at a map of that later. So you might wonder why it's called El Nino. So El Nino is Spanish for the boy. It can be translated as the small one. It's an odd name for a global phenomenon that adversely affects millions of people. It's related to the timing during the year. So El Nino is what the Ecuadorian and Peruvian fishermen who first used the name called the baby Jesus from Christianity. And so they were referencing the fact that a big change in the weather came right around Christmas time. So in December, just in the turn from over December, January, February. The term El Nino referred to a warm coastal current primarily that appears along the shoreline. That's the change in the upwelling along Ecuador and Peru. And it would change the weather that make those shores. It's a little bit of a mixed blessing though, because it also changes the precipitation patterns there and the anchovy catches. And just to convince you that this timing is about right, here are a bunch of different El Nino events just superimposed on each other. And you can see that November, January, March, you can see that the peak of the El Nino is right in here between around December time. All right. So what does the El Nino look like if we go back to that cartoon? We have a flatter thermocline. We have warm water all the way across the Pacific. We have a different wind pattern. It's now the Walker circulation is converging over this central Pacific location to cause convection, precipitation here in the middle of the Pacific, not on the western side. And we have much weaker or reversed winds, reversed or even turned off winds, which means we have much less upwelling in both the coastal currents and along the equator. La Nina, the flip side, which is a little bit of a joke. So La Nina is the Spanish word for the little girl. Instead of the little boy being this, the little girl is this. That has no religious root. It's just the scientists who discovered that there were two modes to this system decided that they needed an opposite condition. It's not quite opposite, but it is opposing in some ways. And under La Nina, the Walker circulation is strengthened. The thermocline tilt is steeper. The winds are stronger. The air-sea temperature, the east to west temperature gradient is stronger, and the convection is very intense and sometimes actually ends up not over the ocean, but ends up over Australia and the maritime continent, Indonesia, New Guinea over here, and can lead to enormous flooding. So here are the three conditions. And the key element here is the Bjerknes feedback, which means the wind leads to the tilting of the thermocline, and the tilting of the thermocline leads to this cold and warm temperature pattern, which strengthens or weakens the Walker circulation, which then leads to more or less tilting of the thermocline, which leads to bigger temperature gradients. So La Nina, stronger temperature gradients, stronger winds, more steeply tilted thermocline, stronger Walker circulation. El Nino, less tilt of the thermocline, less winds, less SST gradient, less Walker circulation. Okay, so here's a typical El Nino just shown in terms of a more simple projection. These temperature anomalies are kind of 2 degrees or so. This is a 91 one. This one is a little bit more centrally located than the one we looked at for the 97. There's some variation in the east-west. There is a school of thought that there is such a thing as the central El Nino or the Molokai El Nino versus the eastern El Nino. But if you look carefully at the records, the center of action is kind of a continuous variable rather than two different kinds of El Nino. There's not enough evidence to say that it's a bimodal distribution. It's just a continuous distribution of centers of action across the central to eastern Pacific. Here's the power spectrum over observations over, this is from a paper a few years ago, which shows that you have basically a lot of energy in between 2 to 7 years. The autocorrelation looks like this. So if you have an El Nino one year, you tend to have a La Nina the following year, about 24 months later, nothing. And then the following year, you might have the opposite. That is the typical pattern. The persistence of El Nino versus La Nina is not symmetric. So that's something to keep in mind, but this is the autocorrelation over all the features. And then this is showing you that the variability really is centered around November, December, January, at least in terms of sea surface temperature squared in Nino 3. We'll say what Nino 3 is in a second. And here's a typical La Nina, which looks about the same, -2 degrees. Still, this cold tongue is intensified. And again, the autocorrelation variance look like that. And this is just showing the RMS of the SST anomaly, which shows that the connection over here to the Peru current and the Peru upwelling system is a little bit more intense. Here are the Nino Indices, which are these boxes for averaging winds or sea surface temperature in that you'll sometimes see described. Here's the Nino 3 box, the Nino 2 box, the Nino 1 box, the Nino 4 box, and the Nino 3.4 box, which is like half of the 4 box and half of the 3 box, is the red one. 5 and 6 are other ones that tend to indicate the precursors leading into an El Nino. El Nino, depending on whether it's more central or more eastern, tends to be centered in either box 3.4 or box 3. So El Nino is the warm anomaly, La Nina is the cold, and Enso is the El Nino / Southern Oscillation, which is the joint pattern of winds and SST variability. The oscillation itself tended to be, Enso is used for both the positive and negative patterns. And the Southern Oscillation is a wind and air pressure anomalies that are strongly correlated. So let's see how that works. So here's the Southern Oscillation Index, which is taken into sea level pressure difference between Darwin over here and Tahiti over here. So you can see that there are these, during a big event, there might be a big pressure difference between those two, which is related to the Walker circulation, ascending here and descending here. Great. And so here's the Southern Oscillation Index, which is just the pressure difference between those in time. And then up here is El Nino. And you can see that for the Nino 3.4 index, that's the sea surface temperature in the 3.4 box, it's warm at the same time that this pattern is low. And then the kind of anomalies without much signal, then warm, low. So the negative here is weaker winds, weaker easterly winds, and the positive here is stronger easterly winds. So here's a big La Nina, which goes the opposite way. And then here's some series of small El Ninos, big El Nino, La Nina, etc. So this feedback pattern of more wind leading to more SST difference and less wind leading to less SST difference was proposed by Jakob Bjerknes in a paper in the, I think in the 60s. So that's what's important about this being a positive feedback. More wind leads to more SST, which leads to more wind, which leads to more SST, is that once you get into one of these patterns, they'll tend to self-reinforce. And so this explains why an El Nino, once it gets started, or a La Nina, once it gets started, tends to stay in place. So interestingly, once one is started, the question is not what keeps it there. The Bjerknes feedback is what keeps it there. The question is what causes it to turn off. So you need a second phenomenon to turn it off. And of course, Enso is not just the SST. It's got a lot of other features going along with it. Combination of Ekman and Sverdrup is part of the thermocline tilt and depth as well. And the Bjerknes feedback also is invoked for thinking about changes in the mean state of the Pacific, not just this variability. Okay, so let's think about how Kelvin and Rossby waves play into this game. Suppose we have a wind anomaly kind of in the middle, like sort of in the Nino 4 box. We'd expect Kelvin waves to run out eastward and Rossby waves to run out westward, roughly. And so this is a little thought experiment. What if you did that? What if you put a blast of wind right here in the middle? Here are the Rossby waves. They're slightly off equator because that's the symmetric shape a Rossby wave would take around the equator. And then here is the Kelvin wave heading east. So the Kelvin wave heads east, it sets up, it would be setting up an El Nino around now. And then these Rossby waves have actually reflected, oops, sorry, it goes this way. Rossby waves in time go over to the western side, then reflect and come back as a Kelvin wave. And then when the Kelvin wave arrives, it quenches the El Nino. So here's the El Nino forming, staying, being reflected back as Rossby waves, but the returning Kelvin wave is actually quenching that El Nino or La Nina as it was. This mechanism is called the delayed oscillator. The idea is that you get one wave that sets up the signal, and then you are delayed while you're waiting for this other wave to reflect off the western side and come back and then change the phase. It's a little bit clearer if you actually look in a Hobmuller diagram that's wrapped around like this. This is from Antoinetta Capitondi's work. So here's the first transect, then second is during the reflection, and then third is coming back on the equator. So we see the Rossby waves propagating from east to west, like this. Then when you get to this reflection part of the cycle, they very quickly, anomalies very quickly propagate from 10 north down to the equator, and then they shoot off across the equator as Kelvin waves. One thing to notice from this, of course, is that, so this distance from 100 west to, whatever, 240 or something, is the same range as roughly this one is, except it goes much, much faster as a Kelvin wave than it does as a Rossby wave. And that's from our dispersion relation that we're used to. This 10 north to 0 is a much shorter transect, so it's not so surprising that it crosses that quickly. But you can see that the anomalies, this is actually showing, I believe it's sea surface height. Should be sea surface height. The anomalies are preserving their signature when they are transitioning between being a sea surface high to sea surface high to sea surface high, and so on. And when they reach over here, all the way on the eastern side, that's when they set up an El Nino or a La Nina, and you can see how they've kind of deepened into a new phenomenon that appears once they arrive at the coast. This is from a model, by the way. This is from the predecessor to the CESM model. Let's see what it looks like in real observations. The top are the winds, the middle is sea surface height, and the bottom is sea surface temperature. You can see that Kelvin wave, look at it, zinging across, and it gets there, it sets up a sea surface high anomaly, and you can see that it's warming up in sea surface temperature as well. So here comes the Kelvin wave, and as it does, when it arrives, it sets up, and the sea surface temperature starts to warm just as it's arriving there. The winds, if you can see them, as the winds are kind of doing all kinds of crazy things. But once the Kelvin wave gets set up and the sea surface temperature arrives, you can see that there's a kind of a low anomaly of winds right along the equator. So that's the 1997, 1998 El Nino being set up. Okay, cool. How does the sphere-drift transport relate to this? Well, the sphere-drift transport really makes sense to evaluate a little bit off the equator. And it tells you that if you have a wind stress like this, then the wind stress anomaly like this, I should say, when you have an El Nino, then you would, if this anomaly and then you have zero anomaly off, you get a curl of the wind stress, and that curl of the wind stress would tend to pump surface water, or, well, it doesn't, sphere-drift transport doesn't actually require whether it's surface or deep, but from the Ekman transport, we know that it should be surface water getting pumped off of the equator like this. And if that's the case, then you will tend to remove any warm anomaly that you have, but you'll also tend to make the whole of the thermocline a little bit shallower. You pump this surface water out, you're going to bring the thermocline. The thermocline has an anomalous weakened tilt. So this is just showing the anomaly. So from this, now you go to a normal thermocline tilt condition in phase 2 with no anomaly in temperature, in wind stress, no anomaly in temperature, and the thermocline is a little bit too shallow. So now what happens when it's too shallow? Well, if you get a wind anomaly, then you could get a sphere-drift transport that brings it back in and brings it down, and that's what a La Nina looks like, which is a cold sea surface temperature anomaly. So sea surface, the thermocline over here is anomalously close to the surface. And now you get a fourth mode, which is like a neutral mode with a deep thermocline. So the concept of this recharge-discharge oscillator by Sarita and McFadden, these two scientists, implies that there are two different ways to be neutral. There's neutral with a deep thermocline, and there's neutral with a shallow thermocline. It's not, this is kind of a schematic of how it works, but actually you can see this in the observations as shown by an important paper by Billy Kessler shown over here. If you map the depth of the thermocline, or the depth of the 20 degree C isotherm versus the sea surface temperature. So if we start in, I think 82 is about when this starts. Start over here, it tends to go around, and then around, and then around, and then around, and then around. And what this means, if it's going in this direction, that means your recharge phase tends to predict an El Nino, which tends to predict a discharge phase, which tends to predict a La Nina, which tends to predict a recharge phase. So it really does move like this. around and around in these circuits. This kind of nonlinear phase space trajectories is something that you expect if El Nino behaves as a nearly linear system. It's not a linear system, but the wave properties of it have some linear characteristics. And so this is kind of an interesting way of seeing at least some aspects of the linearity peeking through in the end. How do we get this kind of data? Well, there's actually been an observing network, which was originally just in the Pacific called the Tau array, but then it got expanded to be the Triton Tau array. There's an Atlantic version called the Parada array and an Indian Ocean version called the Rama array. All of these tropical ocean monitoring systems can all be grabbed and downloaded from the PMEL website, which is quite an amazing thing. So these are all moored buoys. So these are moorings that are permanent. It's extremely expensive to put them out because you have to service them from land. And they are actually all on the satellite network. So they're radioing home the conditions of each of these buoys all the time. So you can get up-to-date data from this array. And why do you need up-to-date data? It's because El Nino is such a huge deal to predict. And similarly, Atlantic variability or Indian Ocean variability is so important for the weather conditions that this is important part of the whole seasonal weather forecasting system. So if you have those, they not only have surface measurements, but they have subsurface measurements. And so this little movie, once it gets rolling, is going to show us what happens subsurface. So you can see the sea surface high. So we were seeing a thermocline anomaly. So the thermocline is getting warm, the surface is getting warm, the surface is getting high as that Kelvin wave shoots along both at the surface and along the thermocline. There's the peak of the El Nino right there. And now we're seeing the La Nina follow it up, where the opposite sign of anomaly comes in, leading to a cold sea surface temperature anomaly. And so here it is in sea surface height, and here it is. This is a movie as well. This is two different El Ninos getting set up. There goes that Kelvin wave. There goes a Kelvin wave here in the 2015-26 one, 15 one, and you can see how they're both setting up into this pattern of sea surface high. The 2015-2016 might be a little more centrally located than the 97-98. There's a lot of differences between them, but the Kelvin wave signal and the Rossby wave signals are really apparent in this signature, and then a following Kelvin wave that zooms up afterwards. Oh, and this video, when I grabbed it, was actually in 2016, so we couldn't see the whole completion of the terminating Kelvin wave in this case. The first successful model for predicting Enso was called the Keynesiviac model from Mark Kane and Steve Ziviak. And it's important that it is a coupled model, so it involves a simple atmospheric model connected to an ocean model that has the ability to do these thermocline dynamics. Since that model, there have been lots and lots of models that are being trained to do this. Here is an example of an ensemble from a couple of years ago. You can go look this up if you want. Right now on the IRI CPC, you can go and look at what the anomaly has been to date, and then what the projections are for the next year and a half or so. You can see that the projections are not always in agreement. Each of these is a different kind of model, and some of them are statistical, some of them are dynamical, like the Keynesiviac model. There's a whole lot of there's a whole cottage industry in trying to make these projections because there's a lot of money involved in it. This is what the teleconnections patterns. Remember, we said the teleconnections are the patterns where the whole global weather is changed by the presence of an El Nino. So this is an example. So as we expect, right over the convection zone, it's going to be wet and it's going to be warm. That's not so a surprise. Wet and warm maybe over the Peruvian, Ecuadorian upwelling as well. Maybe not a surprise, but dry in this bound around it, because this is also an aspect of the Walker circulation. And then there's something else called the P&A pattern, which involves this kind of, this involves the jet stream and deviations in the jet stream up here, where it's warm, Can be wet and cool here, leading to anomalous precipitation in the Gulf of Mexico and in Texas, and then dry over here in Brazil. Lots of interesting patterns. Sometimes these farther ones are also, I think this is only showing statistically significant teleconnections, but this is a lot of interesting stuff here. Teleconnections are probably less stable than El Nino itself under climate change. So even though El Nino may not change under climate change, its impacts almost certainly do change under climate change, because the conditions up here that are leading to this warm anomaly, say, might be substantially different if this part of the world had a different mean state due to climate change. There is a theory that in the Pliocene, El Nino might have become permanent, or at least the mean state in the Pliocene might have looked like an El Nino all the time. This is some of the evidence for this. And Peter Molnar is a person who's been thinking about this idea for a long time. However, it turns out if you run this in models, you don't really get the sense that this was a permanent El Nino. There's still variability. It's just that the mean state looks more like an El Nino with a deeper thermocline, less winds at the surface, less of an east-west temperature gradient. Which is basically what's being shown here, is that the Western Pacific versus Eastern Pacific is changing as we enter the Pleistocene. Okay, what about El Nino in the future? Is that permanent El Nino a decent model for what it's going to be like in the future? Well, in the future, we expect a warmer world. It's unclear whether this will shift the tropical Pacific toward an El Nino-like state. The recharge-discharge theory tends to indicate yes. But actually, if you set this up in models, it's extremely difficult to figure out whether the models are predicting a stronger or weaker El Nino. And my first PhD student, Sam Stevenson, for her PhD, actually showed that the amount of observations you would need, or the length of simulations that you would need, are much longer than expected. So at the time, a lot of the early disagreement among models was probably just due to the fact that they had not run their simulations long enough. And this is that point that I was making before about teleconnections being as stable as Enso. So a lot of work has been done on this. We still don't have a clean explanation as to whether we expect El Nino to get stronger or weaker in the future, because El Nino itself, in terms of the sea surface temperature, to get stronger or weaker in the future, because we don't really, the models tend to disagree about what it's going to do. What the models don't disagree about is they don't disagree that the teleconnections are not going to change. They agree that teleconnections are going to change, and in particular, the wet and dry conditions that have to do with El Nino and La Nina are going to get more intense. That's a fairly clear prediction. On longer time scales, there's something called the Pacific Decadal Oscillation, which involves a lot more than North Pacific, but also involves an important part of the Equatorial Pacific, but a wider swath of it. It's not terribly clear if this is actually a totally different phenomenon than El Nino, in that it also involves the Bjerknes feedback, but it is a kind of decadal signature rather than a 2 to 7 year signature. All right, and so it's intrinsically air-sea. It's a coupled complex phenomenon. Features chaotic, stochastic, and thermodynamic elements. Equatorial ocean waves, Kelvin and Rossby, are there, but they're not the whole story. The sphere drip transfer is this concept of the recharge-discharge oscillator, plays an important role, but it's also not the whole story. And the Bjerknes feedback plays an important role, but it doesn't explain why there's an oscillation. It just explains why these features persist when they're there. All right, thanks very much.